Okay, so by request, I'm going to do a couple of friction problems where we have a block and the block is on a surface. There's friction on the surface and it's being pulled by a specified force. Okay, so we have a 10 kilogram block and it's being pulled by 50 newtons of force, and we've got a coefficient of static friction of 0.5 and a coefficient of kinetic friction, that's sliding, of 0.4. And we're going to find the acceleration of this block. We're then going to do the same thing if we pull it at an angle upward, an angle downward, and then a steeper angle downward. Okay, so we're finding the acceleration. I'm going to draw a free body diagram of the block. We have gravity pulling it down. We've got a normal force pushing it up. And we have an applied force of 50 newtons pulling it forward. It's 10 kilograms, so the force of gravity is 98 newtons. The normal force, which is going to counteract the force of gravity, is also 98 newtons. And we have the force of friction pulling it back. Now the force of friction, let's assume this is sliding. If we can assume it's sliding, the force of friction is going to be mu k times 98. Now, we're going to assume it's sliding, but when we're done our calculation, if it is accelerating this way, that is, if we end up with a net force going that way, then we realize that assumption was incorrect and it's staying still. There's a little more to it than that, and I'll clarify that point after, because there could be such a high coefficient of static friction that there wasn't enough for it to get moving in the first place. But if it was made to move, then it would be able to slide. Okay, so we have a normal force of 98, and we're going to multiply that by our coefficient of friction, which is 0.4, giving us a force of friction of 39.2. So the force of friction is 39.2 newtons. You see the way I did that? The force of friction is the coefficient of friction multiplied by the normal force. Now in a problem like this, the magnitude of the normal force is equal to the magnitude of the force of gravity. So it could be tempting to always use the force of gravity. However, don't. You're going to see in the next couple of problems that it doesn't work there. The net force, which we never draw as an arrow on the block, we draw it separate. The net force is going to be this way. You can see gravity and the normal force cancel each other out. We have applied force of 50 newtons and friction of 39.2 pulling back. So the net force is 50 minus 39.2, which is 10.8. So we have 10.8 newtons pulling the block forward. And then the acceleration we'll just divide by 10. Our acceleration is the net force over mass, because F net equals ma. The acceleration is 10.8 over 10, which is 1.08 meters per second squared. And that's forward, right? Because this is forward, if we call that forward. So to recap, given this problem here, and we assume that that's on a surface, we do a free body diagram. We have an applied force of 50 newtons forward. We have 98 newtons of gravity. We have 98 newtons of normal force pushing it up. That normal force times our coefficient of friction gives us the force of friction. And then when we consider all the forces that balance, what's left over is 10.8 newtons forward. We divide it by mass to get our acceleration going forward. I'm now going to solve the problem when we're on a bit of an angle. So let's say I've got 10 kilograms. It's still a force of 50 newtons. But it's at an angle 30 degrees above the horizon. So now my free body diagram, we're going to have gravity. See this applied force? I'm going to break it into two components. We have an applied force component that's going forward. I'm going to call that FA parallel because it's parallel to the surface that this is on. So that doesn't say fall, that says FA, and then that's two parallel lines indicating it's parallel. Upward, I've got FA perpendicular. So look again here. My applied force is going this way. I have a component that is parallel to the surface that this block is sitting on, and I have a component that is perpendicular. So having a force at that angle, it is the same as if I had a force going directly upward and a force going directly forward. We also have a normal force because this is sitting on a surface. And we have a force of friction pushing back. Now, in the previous example, the only vertical forces were gravity and the normal force, so they were equal to each other. However, if I'm sliding my calculator along and I pull upward as I slide it, I've reduced the normal force. The normal force is how much squeeze there is between the surface and the object that's sitting on the surface. By pulling upward, I'm reducing that squeeze. And the effect of that is I'll be reducing the friction. Okay, so all we need now is some magnitudes here. This is 10 kilograms, so the force of gravity is 98 newtons. Again, that's 9.8 times mass. The normal force, I don't know yet, because the normal force plus this perpendicular component of the applied force will balance the 98. By pulling up on the block, I've reduced the normal force. The normal force is the squeeze between the block and the surface upon which it sits. So let's figure out what this is here. I've got 50 newtons at an angle of 30 degrees. So this is going to be 50 sine 30, and this is going to be 50 cos 30. So 50 sine 30 is 25, and 50 cos 30 is 43.3. So my upward force here is 25 newtons. My forward force is 43.3 newtons. Now my normal force plus 25 is equal to 98. So I'm going to take 98 and subtract 25. It's 73. So the normal force is 73 newtons. So to clarify how I did that, if we've got 98 down and we've got 25 up, how much more do we need up to counterbalance that? If you end up with a negative number for your normal force, what that means is there's such an upward force from the applied force that the block is lifted into the air. However, in this case, you just take your force of gravity, subtract the upward component of the applied force, and that'll give you the normal force. So the normal force plus the upward component of the applied force add up to counter gravity. Okay, now what's my force of friction? Force of friction is going to be the coefficient, which is 0.4, times the normal force, which is 73. $29.2. So now my net force is the parallel component of my applied force minus my force of friction. So that's 43.3 minus 29.2. And that's 14.1. My acceleration is the force, my net force over my mass. So that's going to be 14 over 10. It's 1.41. So notice, compared to pulling it directly forward, when we pull it upward and forward, we actually have a greater acceleration. We have less of a parallel component of force pulling it forward, but by pulling it upward, we're reducing friction. And if the coefficient of friction is high enough, then reducing friction is more important than pulling it forward to contribute to its overall acceleration. Now consider a case where we're pulling downward on the block. So let's say we're pulling downward at an angle of 25 degrees. We still have our 10 kilogram block. So my free body diagram, I now have a force of gravity pulling it down. I have a perpendicular component of my applied force. Now it's going down because I'm pulling it on an angle downward. The normal force will actually be greater because it now has to combat gravity and the applied force. In the previous example, the normal force plus the applied force was equal to gravity, but now gravity plus the applied force is equal to the normal force. It all depends on which way we're pulling or pushing. Over here we have a applied force parallel to the surface, and pushing back we've got friction. And this is the same magnitude, so our force is still 50 newtons. So if we have 50 newtons here, at an angle of 25 there is an angle of 25 here. So this is going to be 50 sine 25 and 50 cos 25. So this is 45.3 and this is 21.1. Gravity, that's 10 kilograms, so gravity's 98. So now the normal force, I'm going to add those two. So it's going to be 98 plus 21.1. 119.1. Now my force of friction is 0.4 times the normal force. Because remember, our coefficient of kinetic friction here was 0.4. My force of friction is 0.4 times 1, 19.1. $47.64. Okay, now look at this. We have a force of friction of 47.64, and we have an applied force of 45. So what this implies is that our net force is going to the left. Friction is greater than the parallel component of our applied force. It's greater by 47.6 minus 45.3 is 2.3. So we have a net force of 2.34 newtons to the left. Friction opposes motion. So to write this down, we would have to clarify that that is only valid if this is sliding to the right. If the block was sliding to the right initially, before the circumstances of the analysis of this question, then we can have friction opposing that motion. We have a block that is slowing down. Let me try and clarify that. So we have a block. We're pulling forward and downward here. It's on a surface. You've got gravity pulling it down. You've got a normal force pushing it up. And from all of our analysis here, we've determined that we have a force of friction, and that force of friction is greater than the forward parallel component of our applied force. That is possible, but it's only possible if the block is sliding forward because it was sliding forward previously due to other forces. If the block was already sliding forward, it could be slowing down. So we have some initial velocity going this way, and we have an acceleration that's going the other way as the block slows down. Despite the fact that we're pulling it forward, it's slowing down as it moves forward until it stops. When it stops, there's enough friction that that block will remain at rest.